two wildly different ways. We were just talking about exhaustive coverage before. NACLs have to cover everything in the universe that's possible. ERC stands for exhaustive rule coverage. ERC. But there are two wildly different ways. There's actually two ways to set up your NACL. Did you know that? So here's the first way. You can have one rule which allows the majority of traffic. Then you add a few more rules, but those are deny rules. You distinguish a minority of individuals who are to be denied access. And just note that those pinpointed individuals may well be covered by the allow rule, but the allow rule doesn't take effect on them because the deny rule is given priority. It will be a lower number. So that's the first way of setting up your NACL. You have one rule which allows the majority of traffic. You have a few deny rules. On a second approach, a rule denies the majority of traffic. Then you add a few more rules. However, these are allow rules. You distinguish a minority of individuals to allow access to. Note how these pinpointed malicious actors may well be covered by the big deny rule, but the deny rule does not take effect on them because the allow rule is given priority. And that's the second way of setting up your NACL. So a deny rule denying the majority of traffic. Now, both of these approaches involve the majority being treated one way and a distinguished minority who are treated differently. The differences between the two approaches may be said to align with the distinction between a deny list and an allow list. Fair enough? Fair. When the distinguished minority are allowed, we have an allow list. When the distinguished minority are denied, we have a deny list. However, we should be cautious here, as we've noted. The distinction between allow list and deny list is couched in this distinction between explicit and implicit reference. So, in other words, an allow list is in place when allowed packets are explicitly referred to. So that's what we mean, putting it in terms of explicitly. And a deny list is in place when denied packets are explicitly referred to. A packet being explicitly referred to is often taken to imply that there's a rule which covers it. And that seems perfectly reasonable. Fair enough again. But a belief which then tends to follow soon after is this. People think that not being explicitly referred to involves not being covered by a rule. And now you've overstepped the mark. A deny list is a list which consists solely of rules pinpointing denied entities, and vice versa for an allow list. However, that's not how NACLs work. When you use a NACL as a deny list, something about that doesn't ring true. NACLs are irksome, ERC, exhaustive rule coverage. Remember, NACLs are such that every entity must be accounted for by a rule. So even if you are pinpointing individuals to deny a deny list strategy, the list of rules won't only be rules pinpointing denied entities. There must actually be a rule to cover the people allowed, or the principals allowed. So use the term deny list if you like, but remember that any notion of implicit reference to allowed entities shouldn't mean that you don't need to have any rules covering the allowed entities. Okay, so don't think that because you're implicitly referring, you have no rules. You do need rules. Everything in the universe must and will be covered by a rule with a NACL. This point about the existence of the rules is important to appreciate with NACLs. We'll soon look at security groups, where there's an interesting divergence on this point. Security groups. Security groups do not work at the level of the subnet as NACLs do. Security groups protect elastic network interfaces. Often they'll simply be said to protect EC2 instances, since every EC2 instance must have at least one elastic network interface. On top of this disagreement over what is to be protected, is it an ENI, is it a subnet, SGs have two features which NACLs don't have. One, allow exclusivity, and statefulness. SGs cannot use deny rules. They exclusively use allow rules. This firewall, this SG, has allow exclusivity. SGs are also stateful. What does it mean to be stateful? It means that the firewall remembers events that have occurred previously. Consider a quick analogy. Consider the remote control used to change the volume on your television set. Suppose the volume has 20 possible values. At 2 it is barely audible, and 16 is a comfortable volume. Suppose you want to raise the volume to 17 because someone is drilling next door. The volume is currently at 16. Fortunately, a single press of the increase volume button is required, just once, to get from 16 to 17. And that is because the television set is stateful. It remembers that the current value is 16. If the television had no state, you would have to communicate 17 to the television. Perhaps you'd do that by pressing the button 17 times. Then, to notch up the volume to 18, you'd have to press the button 18 times on top of the 17 presses you had previously given it. But of course, even that, it is somewhat stateful because it remembers that this is the second press, this is the third press, and so on, all the way up to 17. SGs might be called directionally stateful. This is because SGs remember a packet that was allowed to pass once and allows it to traverse the boundary one more time. So if a particular packet was allowed to travel inwards to an EC2 instance, it will be allowed to travel outwards, even if there's no rule that explicitly allows such outbound traffic. And similarly, if some packet is allowed out by a rule, it will be allowed back in. EC2 instances with their ENIs, or elastic network interfaces, sit within particular subnetworks. Therefore, we can say that SGs are an inner, intelligent, instance-level firewall. And each of these two SG properties, allow exclusivity and statefulness, often give rise to some false beliefs. Allow exclusivity clearly means that it will be hard for us to pinpoint individuals that we want to deny. There's no deny rule for us to use. The SG forces us to install an allow rule which covers any entity which we want to traverse the boundary of our EC2 instance. It thus seems that an SG is more aptly suited to an allow list approach than a deny list one. The exhaustive rule coverage of those irksome NACLs does not hold with SGs. It's true that every entity in the universe will be either allowed or denied by the firewall. However, there's no middle ground. However, ERC states that rules achieve that exhaustive coverage. Every entity is accounted for with SGs, yes, but there is not a rule to account for every entity with security groups. How does allow exclusivity then lead to a false belief? Well, it leads to the belief, and this is false belief 1, that NACLs are for deny listing, that their purpose is for deny listing. The thought is that, and maybe this isn't a completely false belief, actually. Yes, it may actually be a maybe there is a sense in which the purpose of a NACL is deny listing. But as a sort of proper practical principle. But the point I'm going to make here is that there's nothing, if we're looking at it in a completely neutral scientific way, they're not intrinsically deny lists. That's at least the point that I'm going to make. So the thought is that SGs and NACLs are opposites. This is the thought some people have. And the argument is as follows. Allow exclusivity suits a firewall for allow listing. SGs are good for allow listing. Now, if you're not suited to allow listing, then you must be suited to deny listing. Well, NACLs lack allow exclusivity. Therefore, NACLs must be suited to deny listing. The above argument takes various guises. For example, NACLs might be called default allow, to contrast them with security groups, which are default deny. That's all lovely, but that's an oversimplification. If you examine the argument above, it assumes that the only way to be good at allow listing is by possessing this allow exclusivity, the capability to only use allow rules. But it's not the only way. It's not the only way of being good at allow listing. You can deploy an allow list with a NACL. You'd simply have one rule which denies the majority of traffic. Then, to pinpoint entities to allow into the subnetwork, you would install an allow rule as well. And the allow rules would have lower numbers than the deny rule. And lower numbers are lucky and they get priority, and so the distinguished minority would be allowed in through the NACL. It's an allow list. Therefore, NACLs can be used to allow list. SGs certainly have allow exclusivity, and this might suit them for allow listing. Fine. But don't put NACLs in a box. These firewalls at the subnet level remain flexible and adaptable. They can be configured as deny lists or allow lists. So in this way, allow exclusivity leads to the false belief that NACLs are only for deny listing. Now let's look at how the statefulness of SGs leads to a false belief. Because SGs are directionally stateful, when you look at the list of rules, what you see is smart, clean and tidy. Loose ends are tied up for you. There are not sprawling arrays of bountiful, bounded rules. Any inbound traffic which is allowed will have its exit arranged for. And if your EC2 instance needs to initiate outbound traffic, its return will be arranged for. A rule doesn't need to exist for the return. This is because the SG can comprehend the notion of a request and a response. These are rich concepts. Packets are not merely moving in one direction. The SG can think about, in scare quotes, whether this is the initiation of something or not. Statefulness can lead to this belief. The SG has no need for inbound rules as well as outbound rules. You might actually believe that. Strangely, you can have the belief creep up on you, perhaps unconsciously, that security groups only have inbound rules. Footnote: why does that belief arise? Security groups only have inbound rules. Perhaps the thought is as follows. First, threats come from outside rather than inside. That's almost the definition of a threat. Things that come from in, we tend to call things like vulnerabilities. They're internal defects in the nature of something. SGs have a general play it safe culture. After all, when you have a security group provided to you by default, which you do when you launch an instance on EC2, it will block all inbound traffic. So there's this argument that there's a general philosophy of play it safe. So when security groups are said to have an implicit deny, this must be for inbound traffic. Well, that's a start, but that doesn't result in false belief too. Fine, so now let's add to this the fact that SGs are often pre-configured with a rule. And this rule allows all outbound access. I've called it the bias for action rule before. And so textbooks will write things like, traffic is allowed out by default, and so on. And that's true after all. There is a pre-installed rule to let the EC2 instance exert itself on the world. Recall that SGs have an implicit deny. Well, that can't be for outbound traffic, that implicit deny. After all, there's a pre-installed rule, exert on the world. Let the EC2 instance make requests outbound from itself. So the implicit deny idea must only cover the inbound traffic. Now, if SGs are directionally stateful, we don't need pairs of rules, inbound and outbound. We know that SGs deny by default, and this is caused by the sort of rules they're capable of possessing. If SGs don't allow inbound traffic by default, then this must be caused by the sort of rules they're capable of possessing. They're just not capable of having inbound rules. So that's perhaps the thinking. It's erroneous thinking, to be clear. So if SGs don't allow inbound traffic by default, then this must be caused by the sorts of rules they're capable of possessing. Right? They're just not capable of having inbound rules in the same way that security groups are not capable of having deny rules. But yeah, and so that might lead to the belief that SG has no need for both types, both sorts of rule, both inbound and both outbound. So here's a extract from a white paper. You can choose whether to specify security groups when you launch an instance, or associate the instance with a security group at a later time. All internet traffic to a security group is implicitly denied unless you create an allow rule to permit the traffic. Perhaps you believe that SGs only have outbound rules. These beliefs reveal a misunderstanding of how sessions work. It works as follows. Response traffic is allowed without any explicit rule on the condition there's been a request. That request could be an inbound flow of traffic to the instance or an outbound flow of traffic to the instance. An outbound flow of traffic from the instance. We don't care which direction the initiation the request is in, and having both inbound and outbound rules is useful and necessary. I allow Amazon.co.uk to post packages into my letterbox provided I've requested it online. If Amazon.co.uk were to start inputting advertising leaflets into my door, that changes things. Now it's spam. That's not acceptable. No session has been established. TCP is said to be a connection-oriented protocol. The connection is what allows this protocol to be stateful, since the duration of the connection underlies both the request and the response. The first stateful firewall arose at Bell Labs from the work of Bill Cheswick and Steve Bellovin. Cheswick joined Bell Labs in 1987, 2 years before the year when the web is usually said to have started, 89. And so Cheswick joined in 87 and developed the first network firewall. These early ones were called packet filterers, and they're similar to the NACL. They work at layer 3 of the OSI model. Then in 1993, 6 years after joining, the stateful firewall emerged. Such firewalls can be thought of as operating at layer 4 of the OSI stack. TCP works at layer 4. The NACL doesn't have the perceptual apparatus to see connections or sessions. It cannot see, as it were, requests and responses, even if it can notice the direction of the packet, inbound or outbound. It can notice that. But the rich concepts of request and response, which require a state in the firewall, are beyond the NACL. So here's a summary of the properties of SGs and NACLs. SGs have allow exclusivity. Only SGs, this left column, are stateful. If we look at the entity protected, well, NACLs protect the subnetwork, the segments making up the VPC. You'll have an ENI protected by a security group, an EC2 instance, an application load balancer. NACLs have what I call exhaustive rule coverage. Everything must be covered by some rule, but there's this priority principle as well with NACLs, which can help resolve which rule is actually going to take place. Rules are numbered. This is what I mean by priority. Rules are numbered. The lower number is lucky, and is higher priority. It's true that a single entity can be covered by multiple rules in a security group. It's true. So we might say that concurrent coverage is possible with security groups and with NACLs. But with security groups, concurrent coverage is not a useful tool. Here we have a set of entities which are allowed, and I've marked out a subset, but they're also allowed because we can only use allow rules with a security group. This just means the fact that we can concurrently cover things with security groups just means a request can be allowed twice, as it were. With SGs, there's no possibility of conflict arriving from a single entity being allowed by one rule and denied by the other. If any rule in an SG allows an entity, then that entity will be allowed. I think that's correct, at least. So we're told, if there is more than one rule for a specific port, Amazon EC2 applies the most permissive rule. The most permissive rule. For example, if you have a rule that allows access to Transmission Control Protocol, Layer 4 remember, TCP, on port 22 from IP address 203.0, and another rule that allows access to TCP port 22 from everyone rather than just that specific IP address, well, then everyone has access to TCP port 22. Okay, we apply the wider rule. So don't just think that because you've seen a rule in an enormous list of SG rules, which pinpoints an individual, allowing them access, you can justifiably say that the SG is very restrictive. You have to do your homework and look at all the rules of the SG. The bigger rule will take priority. That might seem strange to you. 4.7 focusing. There's an interesting parallel between what has happened with load balancers on AWS and what's happened with firewalls. In each area, AWS have developed a resource focused on Layer 4 and one on Layer 7. Both have experienced 4.7 focusing. Since 2009, AWS have had the Elastic Load Balancing product. This is very well established as a product, a service, announced in a triad of services, really, in 2009. The other two in the triad were Auto-Scaling and CloudWatch. Load balancer is sometimes shortened to LB, and this reminds me of cricket. In cricket, a leg by is a rule. It's quite simple. If a ball hits the leg, then runs known as leg bys can be scored. LB. The governing body of cricket is called the International Cricket Council. In this way, LB makes me think not only of load balancing, but also cricket. What's the basic use of load balancers? They distribute traffic. They balance the load amongst things. They distribute traffic to your back-end service. They balance the load. More technically, a load balancer is a proxy since it communicates with the back-end servers on behalf of the client. Is that right? It represents the client. However, yes, yeah. That's what a proxy is. But it might be that we want to refer to a load balancer as representing the server as opposed to representing the client. And sometimes when to distinguish that idea of the server, the thing providing the service being represented, that's sometimes called a reverse proxy. And maybe the load balancers you can use on AWS are more like reverse proxies. Generally, something that represents another thing is a proxy. Load balancers, they're a kind of man in the middle. They have a privileged position in that respect. They can check on the health of the backend servers. If they're unhealthy, the load balancer will not send traffic to them. So straight away we can see that a load balancer reduces the chance of a miserable client. It's more than simply avoiding unbalanced loads. Load balancers help to achieve high availability. A company like PlayStation might decide to run a commercial during a televised cricket match. PlayStation might be allowing orders for a product, and it will have a fleet of back-end servers prepared, and balancing the load between these servers will be an indispensable part of preparing for the flurry of traffic. In 2016, AWS announced that they have a specialized load balancer, and it focuses on layer 7 of the OSI reference model. The OSI reference model sets out 7 layers in the full networking stack. The load balancers available since 2009, they then came to be called classic load balancers, even though many specialized features came with the focused layer 4 load balancers and the focused layer 7 load balancer. Configurable features did continue to be added to the classic load balancer until quite late on. But for revision purposes, there's a good acronym for recalling the 8 funky features which you can find on a classic load balancer. From load balancer, LB, to Cricket, to ICC, PS, DTD. So the 8 features are I for idle timeout, C for cross-zone load balancing, zone referring to an availability zone, C for connection draining, P for proxy protocol, S for sticky sessions, and then DTD. We've got D for desync, desync mitigation mode. Mitigation means making better, reducing the harmful effects of something. So desync is a really bad thing. So there's certain things we can do to mitigate this desync problem. T is for tag. You can tag your load balancer, and the final D is for a domain name for your load balancer. So we've got 2 Ds, one for desync, one for domain, 2 Cs, cross-zone and connection draining. Let's go into some of these quickly. Sticky sessions. If you think about sticky, they don't come apart. It involves the client being sent to the same server. The acronym gets you to this nicely if you think of a horrid, sticky PlayStation controller. The client maintains a session with one particular back-end server. This is achieved using tokens called cookies. So we already had a few things which could be configured on the classic load balancer. And in 2016, the application load balancer was announced. The ALB can make decisions about whether to pass traffic onto the EC2 instances behind it. Because this decision can hinge on internal features of the request itself, it's often said to be able to achieve content-based routing. The content of the request is examined, as opposed to merely formal aspects such as the source and the destination, the protocol. They're sort of features of it, about it, but they're not content. The ALB can examine a portion of the URL which is known as the query string, for example. The beginning of the query string is marked by a question mark character. By convention, the query string consists of a sequence of attribute value pairs, or key value pairs, sort of, but we are going to call them attribute value. Not all URLs have to have a query string. However, all URLs do have a path, or they're more likely to have a path. The path comes before the query string. What does the path look like? You know you're looking at a path because you'll see a sequence of path segments and they are separated by a / character. So take a look at this uniform resource locator, this URL. At the beginning, we name the protocol and we put : // That's called the scheme, the protocol scheme. www is the name of a domain, so is name, and so is com, the commercial domain. So we have www, which is in name, and that is within com. And now we have a / and we're done doing the domain names. Path. We now have the path after this /. You might put .html to show what kind of file we're providing on the web. Is it an HTML file? Hypertext markup language. It's called the file extension, .html. A bit like .jpeg or .png or .doc. We then have a question mark character, and that means that the characters after the question mark are the query string. A string is just a data type, as opposed to an integer, a type of whole number. A string consists of letters, numbers, and other characters. So it's a query string. Query because we use these characters here to answer specific questions that the client might have. They might be interested in only particular search terms, and so that's a parameter, that's something they've specified. So it's called the query string, and it's made up of these attribute value pairs. Sometimes the path component in a URL, remember this /path after the com, it will map onto a path within a file system. This is not always the case. Anyhow, these features of the URL are features which the application load balancer revealed in 2016. It can pay attention to those features of the URL and use them to make a decision about whether to forward traffic to one of the EC2 instances behind it. In 2016, Matt Wood described the ALB as, these are his words, a higher order routing abstraction, which gets the right traffic to the right application component. We might say the ALB is conscious of HTTP headers and HTTP methods. So examples of HTTP methods are, it's a bit of a term of art, are get and put and post. And options, they're usually written in all uppercase, so get, capital G, capital E, capital T. So if you're filling out a form on a website, probably a put or a post request will be sent away from your laptop to the server because you're placing data at the server. Sometimes though, when you use something on the web, you're just reading information, so it's like a get. It's probably a get. So that's what we mean by method. An HTTP header is a field, a special place to specify information within a request. For example, the authentication header. You can put some sort of password there. So they're like, headers are like little pockets where the request can carry specific information for a designated purpose. Practically, the header is a word and then a colon, ... So we might have the authentication header, or the headers related to security tokens and so on. As well as this content-based routing, remember it could look inside the request. What is the path? What is the query string? As well as content-based routing, that application load balancer is capable of authenticating requests, assessing the identity of the person making the request. The ALB makes decisions based on rules. The ALB is a list of rules. Each rule consists of 3 parts. 1, a priority, 2, a condition, and 3, an action. So, for example, a priority, a condition, an action. You can make the condition be that the query string has a particular value, or that the HTTP header, one of the HTTP headers, is a certain way, has a certain value. There are 7 options for the condition at the moment. This is around 2023. You can see the similarity to firewalls. There are 3 possible values for the action. Remember, 3 and action. Redirect, forward, fixed response. What on earth do we mean by fixed response? This actually involves dropping the request and sending a message back to the client. This option might be called get lost. You can use fixed response to send back a code to the client, such as 2xx or 4 something or 500 and something. We all know about the 404 response code when you look for a web page that isn't there. As well as responding with a code, you can attach a custom message such as hello world. Notice how the load balancer is responding immediately. It's not actually doing what it normally does as a middleman, sending the packet onwards to the servers behind it. And we can now see why it's called fixed response. The load balancer, not the EC2 instance behind it, is giving a response, and it's the same each time. So it's called fixed response. But you do think, hold on, what's going on here? This is a load balancer. Surely it should be getting on with what it says on the tin, balance the load. It's not immediately clear why we're having a discussion about various actions. Worse, it's not clear which of the action is just plain old load balancing. We've said you can redirect, forward, or fixed response, which means get lost. The truth is that of the three actions, the central case is forward. That's load balancing. This is forwarding traffic on to a server from the client. The unusual cases are fixed response and redirect. Fixed response involves dropping the packet, and therefore not forwarding it on. The redirect option is, in truth, an example of forwarding. However, it's a special type of forwarding, in which you readily dictate or readily direct the request that it simply must bend to meet your rigid constraints. For example, an HTTP request can be redirected to HTTPS. We've got to use Hypertext Transfer Protocol Secure. In fact, the protocol, HTTPS and HTTP are examples of protocols. That's just one component. There are, in fact, 5 components over which you can exert your idiosyncratic preferences. And for any of these 5 components, you can dictate that this aspect of the request be brought into line with your peculiar preferences. So protocol, you can readily dictate the protocol. The host name, which is the domain name really, you can readily dictate that. The port, you can readily dictate that. The path, you can readily dictate that. And even the query string. 5 things. PHPPQ. I demand that the Queen hear my request, Philip shouts. And as usual, he's told he must queue like everyone else. PHPPQ. And so the ALB can readily dictate requests to adopt a particular protocol, such as HTTPS. The ALB can readily dictate that requests adopt a particular port, 443, which is the port usually used for HTTPS secure, 443. Of course, those 5 components, PHPPQ, they're simply the components that make up the URI, the Uniform Resource Indicator, or locator, as we move from left to right, if you think about it. So PHPPP, can you think what the first P is for? Well, think of a URL. What do we have at the beginning? The protocol. Then we have, after the double / the host name, PHPPQ. The host name, the port, admittedly the port doesn't usually appear in a uniform resource locator that you'll type into your browser. But then we have the / and the path, and we certainly have the query at the end. So that's PHPPQ. They must be this way. This is the URL you'll be familiar with, which appears in the address bar of Google Chrome, for example. If you do choose the action to be one of the redirect sort, which readily dictates that some component be brought into line, you need to specify that at least one of PHPPQ must be bent to your rigid preferences. You can't pick 0 components. Otherwise, the request would come in, match the criteria to be brought into line, match the criteria to be brought into line, ad infinitum. You would create a loop. So you do have to pick one out of PHPPQ. And remember, the 3 P's are for protocol, port, and path. Even though it's PA, it comes third. Protocol, port, and path. I think that under the hood, an ALB action of the redirect sort is a match statement which covers requests which are not yet correct. Strictly, it doesn't even cover requests which are already in line, actually. So it doesn't even cover requests which are already in line with your rigid demands. And that would explain why am I saying that? Well, that would explain why requests which are not or which are already in line, they do not cause an infinite loop, in case you were wondering about that. All this is simply to say that if you select the redirect type of action, then for at least one component of PHPPQ, you must specify something. However, you can certainly allow that only the path gets changed or only the host name gets changed, and so on. So 3 possible actions. Redirect, readily change. Forward, fixed response, FR. So the action element for the ALB, it's not allow or deny in the way it is with Knuckles. The ALB has 3 actions: forward, redirect the traffic, or provide a fixed response. That was the ALB announced in 2016. Then the very next year, September of 2017, the year month school was coming into term was beginning, another specialized load balancer was announced, which instead operates at layer 4. The ALB is at layer 7. The network load balancer is at layer 4. NLB. As well as being at the connection layer, layer 4, this load balancer can deal with larger volumes of traffic. It is designed to handle tens of millions of requests per second while maintaining high throughput at ultra low latency with no effect on your part. Remember, throughput is about the quantities being conveyed per time unit, and low latency is really a measure of time itself. They are different things. So the unspoken assumption is that the classic load balancer, which is just the term for the pre-2016 load balancers, struggled with larger volumes, and Jeff Barr hints as much. In some situations, such as instantaneous failover between AWS regions, or extremely spiky workloads, so you have big differences between how much demand you have, little demand, then big demand. It's not very stable. So in those situations, we've worked with our customers to pre-provision elastic load balancers in anticipation of a traffic surge, because that's what they used to have to do before they brought out the ALB and particularly the NLB. The network load balancer also preserves the IP address of the client initiating the connection, and it provides a static IP address for each of the availability zones over which it operates. These 2 features prove extremely helpful, and we're going to investigate them next time.